exercise 6K, and there's a lot that I want to talk about because having gone over the past 10, 15 years of exams, this is a pretty common type of question. Okay? They're really interested. All of the work we've been doing in vectors is sort of building up to this point. It's culminating here, and it's intersection of planes. And so we've figured out that we can have a plane in 3 dimensions, and we've figured out how to describe that. And so then if we have 2 planes in 3 dimensions, okay, if we have 2 planes in 3 dimensions, it's just like if we have 2 lines in 2 dimensions, okay? But there's 3 instances, and I've listed those there for you. The planes are either going to intersect, okay? So just as a line goes in 2 directions forever, a plane goes in 4 directions everywhere, okay? A plane exists infinitely just as a line does. So the planes are either going to intersect at some point, they're either going to be parallel, so sit above or below one another, or they're going to be coincident, where they exist in the same space. They're the 3 circumstances when we have 2 planes. Okay, so I've said this lesson is going to be a 2-part. The first part of the lesson, we're just going to talk about 2 planes in 3-dimensional space, and in the second part of the lesson, we're going to talk about 3 planes in 3-dimensional space. So, this is the first one we've got. We've got these 2 equations of planes, okay? And if you look at the table above there, I've got the echelon form that occurs when we have that specific geometric interpretation. So what we can do then is we can reduce it to row echelon form and assess which geometric representation do we have, okay? So first, let's write this as an augmented matrix. We're going to have 2, 1, minus 1, and 5, minus 1, 2, 4, and 7. Now I've showed you guys in the video last week how to reduce this to row echelon form on your calculator in sort of one go, but it's not particularly useful for these questions. They often want to just show all your working out. And I will show you a bit later as well how we can do row operations with our calculator. But that's also a bit clunky. All operations with vectors are a bit clunky. All right, so let's process this. So what we want to try and do is get a 0 here, isn't it? All right, so if we try and get a 0 here, what we're going to need is we're going to replace row 2, and we're going to replace it with 1 lot of row 1 plus 2 lots of row 2. All right, so if I'm multiplying this by 2, I've got -2, and when I add them together, it's going to annihilate, and we've got a 0 there. So let's process that. The first row remains the same. And our second row, we're going to have 2 plus -2. We're going to have 2 plus 4. We're going to have minus 1. Excuse me, that's 5, isn't it? It's 1 plus 4. That's 5. We're going to have minus 1 plus 8 will be 7. And we're going to have 5 plus 14 will be 19. Okay? Now we actually can't reduce this any further. If we try to perform another operation, like if we try and do this row, take away this row, we're still going to end up with 3 numbers in this row and 2 numbers in this row. So that's as far as we can take it. So then what we do is we parameterize the result. Anyway, because we've reduced it to row echelon form, we can refer to our table and say, well, which solution do we have here? And it's the top one. All right, we've only obtained 1, 0. We've only obtained 1, 0, which means with 2 planes, it has to be the top result. The planes intersect. They intersect, and when planes intersect, they will inevitably intersect along a line. Okay, you can think about this, it just scales up. 2 lines meet at a point. All right, 2 planes meet along a line. All right, so the planes intersect. So let's find the line where they intersect, and we're going to describe that parametrically. All right, so what we've got here is we've got 5y plus 7z equals 19. That's what that means as equation number 1. So we're going to go let z equal t. That's the parameter we like. And then we've got 5y plus 7t is equal to 19. And we're going to solve that for y. and now we'll solve for x using the top row. We've got 2x plus y, take z, is equal to 5. So I'm just going to rearrange it. Is equal to 5, take away, in brackets 7t on 5, and take away plus z, which is plus t. Now before I divide by 2, I'm just going to collect all of that to simplify it. So what it's going to become, it's going to be what, 25 take 19 plus 7t plus 5t on top of 5. Alright, that's what 2x is. And then, so x is going to be on top of 10, and we can collect this. We've got 25 take 19, that's going to be positive 6. And we've got 7t plus 5t, that's going to be plus 12t. And that can simplify. So, what, 3 plus 6t on 5. Alright, so the equation of the line where these two planes meet has this x coordinate, this y coordinate, and this z coordinate. Alright, they meet along that vector line. Excellent, that's the first one. Okay, let's go on to example 2. Consider the two planes given by 3x plus y take 2z equals 10, and 6x plus 2y take 4z equals k. Okay, determine the values of k for which the planes are parallel and for which they are coincident. So what we're first going to do, to begin with these, all right, to begin with, you're just going to start writing them in augmented matrices and try to reduce them to row echelon form. After a while, we're going to start to see some patterns, and particularly when we get to the next part, we'll point out some patterns. So if we want to reduce this, we're going to try and get a 0 here. That's what we're doing, right? So we're going to replace row 2 with 2 lots of row 1, take row 2, right? I haven't written it as a matrix yet. Let's not do that. 3, 1 minus 2, 10, 6, 2 minus 4, okay. Right, so let's replace row 2 with 2 lots of row 1, take row 2. So 2 times 3 is 6, take 6 is 0. And we'll have 2 take 2 is 0. And we'll have minus 4 take away minus 4 is also 0. And then we'll have 20 take k. Alright, so then the question says, determine the values of k for which the planes are parallel. So if they're going to be parallel, right, we're looking and we have to have that row echelon form. What it means is we have to have a number here. It means it can't be 0. So what that means is that's going to be 0. That's going to be 0. That's going to be 0 if k is 20. So if we want a number there, then k cannot be 20. If k is not 20, then the planes are parallel. Whereas if k equals 20, alright, then we're going to have a 0 there, and the planes are coincident. Alright, so if k was to equal 20, the bottom row would be all zeros, and we would have the third geometric interpretation. Okay, any questions about that so far? Alright, so the other way, like this is how like they like to do it to make sure they can do the row operations manually. Okay, because if you have a variable here, we can't mash it in our calculator. Okay, so we're processing that manually, and then they're asking about a different number of interpretations giving some variable. So that's in 2 planes. Now the other thing you can see here that we should be looking at, this is where I was talking about patterns before. Notice how these two are scalar multiples of one another. Okay? So that means that they're at least parallel, okay? They're going to be coincident if this number is also a scalar multiple with the same constant, okay? So coincident planes have the same equation, right? Whereas parallel planes are going to have a different number here, okay? That being the extension. Okay, let's move on to example 3, and then we're going to pause. So we've got consider the planes, and we've got these two planes here. Show that the point, so I'm going to write them up, x plus y plus 2z equals 3. And plane 2 is x take y plus z equals 6. Show that the point A, which is 9, 0, and minus 3, lies on both planes. Well, a point lies on a plane if it satisfies the equation of the plane. So we're going to check A on plane 1. We're going to plug that coordinate into this equation. We're going to have 9 plus 0 plus 2 times minus 3. And we're going to check if it equals 3. So we're going to process here. We have 9 take 6. We've got 3 equals 3. Therefore, yes, this point lies on the line. Okay, we'll repeat for plane 2. So we're going to have 9 take 0 plus minus 3 equals 6. We're going to have 9 take 3, 6 equals 6. Therefore, yes. Point A is on plane 2 as well. Find the equation of the line of intersection of the two planes. Okay, so now what does that mean? We need to find where they intersect. Well, we're going to reduce it to row echelon form. So we'll start with the matrix. We've got 1, 1, 2, and 3. And we've got 1, minus 1, 1, and 6. We don't need to perform any multiplications here. Let's replace row 2 with row 1, take row 2. It's going to give us 1 take 1. 1 take away minus 1. 2 take away 1. 3 take away 6. Alright, let's go ahead and solve. We're going to let z equal t. Therefore, 2y plus t is minus 3. We're going to get y equals minus 3 take t on 2. And then for x, we've got x equals 3 take y take 2z, which is 3 take away 6 plus 6 plus 3 plus t take 40 on 2. Collect that, you get 9 and minus 3t on 2. Cool. All right, so the equation of the line where these two planes meet has this x value, it has this y value, and it has this z value. All right, find the angle between the two planes. So this was an exercise you guys did while I was away. So the angle between the two planes, just flip back a bit, we'll see the formula there. So it is in 6i. We've got cos theta is the normal of plane 1, dot the normal of plane 2, or the modulus of the normal of plane 1, and the modulus of normal 2. So we've got these two planes, all right? So the normals, so normal 1 is the vector 1, 1, 2, and normal 2 is the vector 1, minus 1, 1. So let's evaluate. We're going to have 1, take 1 plus 2 on. We have the modulus. Here we'll have 2, 6, and 3. Let's evaluate that. So 2 on root 18. 61.8 degrees angle between the two planes. Alright. So we've got the two planes meeting, we've found the angle between them. What's it say to do next? Okay, consider the planes described above and consider the point B which lies on plane 1. Find the distance from B to plane 2 using the distance from a point to a plane formula. Okay, so this is at the tail end of 6H, and it's a formula that you do derive, but I did provide for you in the notes book. So if you're having a look at 6H, it's right at the bottom for our notes book. This one here. I'm going to write it up and we'll write D equals the modulus of okay. So in the context of our problem, all right, the coordinates we've got is point B, which is 3, 0, 0. And the values, so they're the values of x1, y1, and z1, right? Because that's the coordinate. And the values of A, B, C, and D we get from the equation of the plane. Now, what plane is it asking about? It's asking about the distance to plane 2, because point B lies on plane 1. So plane 2 has the equation x take y plus z equals 6. This is the equation of plane 2. X take y plus z equals 6, which means the value, if we're going to write it like how we've got it up here, it's going to be like this, plus z take 6. Alright, so the value of A is 1, the value of B is minus 1, the value of C is positive 1, and the value of D is negative 6. Okay, so it's when you move it all across to one side. We've got all of the values there. We're ready to match it in this formula. So it's going to be the modulus of the A times the x value. So 1 times 3 plus the B times the y value plus the C times the z value plus the d value. Modulus. Okay? All on top of the square root of a squared plus b squared plus c squared. So let's process that. So here we've got 3 take 6. So it's the modulus of minus 3 on root 3. So the distance then is 3 on root 3 units. Alright?
It's root 3 squared, isn't it?
It's an area that would be unit squared.
No, in the formula it's the square root of a squared plus b squared plus c squared.
Oh yeah, that's
So
the
3.
1 plus 1 plus 1.
3 would be squared, wouldn't it?
Substitute in these values.
Oh yeah, yeah.
Alright, so then, okay, last part here. So that's fine, that's the distance from B to the plane, okay? And so that's going to meet the plane at 90 degrees, isn't it? Part 2. Find the shortest distance from B to the line of intersection of the planes. So, I'm going to have to write it out using the words basically. So there's a couple of ways of going about this. I'm going to show you guys the fastest way, because we can use technology to support us a bit. So if we've got, and I'm going to provide a bit of a sketch as well. let's say these are the planes, okay? We've got point B, and we've found that distance. We know that that distance is 3 root 3, and here's the line where they intersect, and we're saying, what's the distance from point B to the line where they intersect, okay? Now, there is an argument to be made using Pythag and a right-angled triangle, but we do need to know, like, this distance here, which would involve finding the foot of the norm. So you could pursue that, right? I think that's going to be long. The other procedure you could use is when we did the distance, the shortest distance from a point to a line. Okay, so that's gone back a few exercises. And what we did is we said, oh, if we have a distance from a point to a line, what we need to do is we need to find, let's call it A, P, and then F or something. We need to find when is AP dot PF equals 0. Alright, so we're finding those direction vectors, finding when the direction vector is equal to 0, that's when it's 90 degrees, and then we're going to evaluate the line PF given that parameter T. Okay, so you can do that. That's how you do it manually. Again, a bit of an elongated process. Let's look at how we can use technology here. So what we have, we've got coordinate B, right? Coordinate B is 3, 0, 0, and we've got the equation of the line. Oh crap, I wrote that. No, I didn't. It's here. So the line is x is 3 plus 6t on 5. Or is that's the first one we did, is it? Does anyone have the line written down that we just did?
9 on 2 take 3 on 2t.
9 on 2 take 3 on 2t. Thank you. That's for x.
Y is minus 3 on 2 take half t.
Take
Half t.
take half t.
And
And
z
then
is t. Yeah.
Okay, so that's the equation of the line where the two planes meet. Now we're saying what's the shortest distance when it's minimized from this point to this line? Okay? Remember, this represents a coordinate for any value of t. So we can come up with an expression involving the distance. Right? The distance is the square root of the x value squared. The x value, take the x value squared. So we're going to have 3 take away t squared. Squared. So we have to perform the subtraction and then square it. Plus the y value, take the y value squared. Square it down here. And then the same with z. And square root. Okay? Now that there is the distance between these 2 points for any value of t. Alright, so it's going to tell you the distance between B and the line at any point along the line. We want to know when it's minimized. So one thing we can do is graph this and G-solve it. Alright, you can graph it and G-solve it. And it's going to list you a G-solve the min, right? So if you graph it, I'm going to bring it up quickly on my laptop. Show you. That's what it looks like. Okay, so it's like a quadratic. Because in the square root, you do have a quadratic. If you were to expand all that and collect it, the leading degree is a squared. Okay, so it is a quadratic, but then we are performing the square root of it. So all that does is square root the maximum, the minimum value. And so you can see a minimum occurs. All right, so there's a minimum there. And when we G-solve it, I've got a set of coordinates. It's minus 0.6 and 1.342. Now one of these is the t value and one of them is the distance. Alright, this is the t value that occurs when the distance is minimized. Okay, why? Because it's a relationship according to t. And this is the distance. So the minimum distance between B and the line is 1.342 meters. Okay, so that's definitely the fastest way to do it. Alright? Unless it wants us to perform some manual process in which we can flip back a few exercises and perform that. Alright, so we'll stop the video there.